We're back for problem 2. This will be problem 2's video solution. I better put this on pen. So problem 2 is a lot like problem 1 in terms of our approach, but at the same time it's a little different because we've got a lot of algebra. So we're supposed to figure out how fast this thing is going at the bottom of the hill in terms of these other variables. Okay? Our first step is still to pick out a system, because we're still in the systems, interactions, model, solve process. So I went ahead and picked out a system there. It should be that block, because that's the only thing that's going to be moving or doing anything exciting. Second part is interactions. We got to draw a free body diagram. So I've got gravity acting down. Again, I just write mg to represent the force of gravity. And then I've got normal force. And this time, no friction. So I don't have any friction acting on this. I just got that stuff. I still need to figure out what direction this thing's going to accelerate. So I think that's going to be down the hill. And so once I know this thing's going to accelerate, it's just a good idea in my diagram to break all the forces up into components parallel to that acceleration, perpendicular to that acceleration. Okay, so normal force is already entirely perpendicular to that acceleration, but gravity, we got to break up into two components as we have done before. So we'll call this force parallel and that force perpendicular. And then we've proven before mathematically that that angle's got to be theta. All right, with that said, we're going to go with, if I want to figure out how big that force parallel is, I can say that either some of you can just jump straight to saying the force parallel is the whole mg times the sine of theta, and others of you would prefer if I said that the sine of theta is again defined as the side opposite of something over the hypotenuse. So that would be the side opposite, force parallel, over the hypotenuse, mg. And then if I just multiply both sides by mg, I'd end up with force parallel equals mg sine theta. All right, with that setup, it kind of makes sense in the force perpendicular. Not that I need to find it in this one necessarily, but if I did, it's mg times the cosine of theta. All right, that's all well and good, but it didn't do me any good yet because it didn't help me get VF. So to find VF, I'm thinking I need to do some kinematic stuff. So I'm just going to say VF is what I'm looking for. V original, I'm assuming is 0. Yep, it's 0 because they told me that. And I don't know acceleration, and I don't know time, but I do know how far I'm going to slide, and that's some distance d. Okay, so to do anything, to get anywhere in this problem, I really need to know either VF, well, I'm trying to find VF, so I really need to know acceleration. Well, that's where this net force and free body diagram stuff comes back into play. If I look at this object, it's going to accelerate down this ramp. So I can solve for that acceleration just by looking at the net force. So I want to say that net force is equal to mass times acceleration in the parallel direction. And I have this force parallel acting down the hill, and it is unbalanced, as in nothing is fighting against this. So that is what's going to cause my object to accelerate. Okay, now cleverly, we just solved for how big force parallel is. It's m times g times the sine of theta, and that equals mass times acceleration in the parallel direction. I didn't give us a mass for this thing because, look at this algebra. If I divide both sides by mass, that mass will cancel out. And so that tells me that my acceleration parallel to the ramp is just g times the sine of theta. Once I know that, I can figure out how fast I'm going at the bottom of the hill, now that I know that this is g sine theta, because I can just say that Vf squared would equal V original squared plus 2 times acceleration times delta x. In this case, I know V original is 0. So my speed at the bottom of the hill, V final, squared, is equal to 2 times my acceleration, which I just found is g sine theta, times the distance this thing's going to slide, which is d. So if I solve for V final, I'll just take a square root and get 2g sine theta times d. That is my final speed at the bottom of the hill. Okay, and it's all done in algebra. They wanted me to find this in terms of theta, d, and g. Well, I've got theta, I've got d, I've got g. G is a fundamental constant. It says in terms of things, fundamental constants, g is just kind of like a given. It's acceleration due to gravity. It's a thing that for us at this point doesn't change. All right, all that mess was part A. Part A. Part B, we're supposed to figure out how much time it takes to get there. Okay, to figure out how much time, I now know VF. I now know V original. I now know A. I'm just looking for T. So I think I would jump to VF equals VO plus AT, and then plug in and solve. So VF minus VO divided by A would equal T. It's not going to come out neat, but it'll come out still. VF is radical 2g d sine of theta, and the acceleration is just g sine theta. So I can leave it like that and say, hey, that's my time. Or if I want to simplify under the radicals and all that kind of stuff, I can do that. But I ended up with a radical in the denominator and coming back to this place anyway. So I think I'll just leave it like this. So this is my answer. That's what time is. And again, it's in terms of d, theta, and g. I only have in here g's, thetas, and d's, and then the number 2. That's fine. Okay, so that's problem number 2. Hopefully it wasn't actually that bad, and this algebra manipulation is getting more familiar to you.